In this last topic, we are looking at computationally intensive methods for statistics, which are commonly known as randomization methods. There are three subtopics. Firstly, describe the differences between randomization methods and their application scenarios. Secondly, apply jackknife method to estimate the confidence interval of a statistic. And finally, apply bootstrapping procedure as an alternative to nonparametric statistical tests. Imagine a case where you have a set of data and regression is performed. The coefficient of determination is 0.9139. But can you find the 95% confidence interval of R2? By extension, can you test whether R2 of 0.9139 is significantly different from the R2 of 0.95? In order to find the 95% confidence interval of R2, you need several R2s in order to get the standard deviation, which is used to determine 95% C. Then by extension, you can then determine whether 0.95 is within 95% C of R2. If 0.95 is within 95% C of R2, then R2 of 0.9139 is not significantly different from 0.95. So the problem is then how to get several R-squares? We can use resampling techniques to generate multiple R-squares. Resampling is based on central limit theorem, which states that the distribution of sample means approximates a normal distribution as the sample size gets larger, regardless what is the shape of the underlying distribution. So, the concept is this. If and only if a sample is representative of the population, which means that a sample is a mini-population. I can resample multiple subsamples from a representative sample. And by central limit theorem, the averages or means of these subsamples is approximately normally distributed. In fact, it is not just the means but any statistic, be it median or what, is approximately normally distributed. There is a lot of information here, take your time to digest. There are two resampling techniques, jackknife and bootstrap. Let's look at jackknife. In reality, jackknife resampling is not randomization as it is the sequentially deleting one observation in the dataset, then recomputing the desired statistic. Hence, jackknife resampling is also known as leave one out resampling. This means that if your data has 10 values, you will have 10 subsamples of 9 values. The first subsample will have the first value left out with the second to the 10th values remaining. The second subsample will have the second value left out with the first value and third to 10th values remaining. And so on. There are two main advantages. Firstly, jackknife resampling can be performed manually even though it can be tedious. Secondly, jackknife resampling always give the same result. You will see why this is the same in our examples later. However, the main disadvantage is that jackknife resampling does not perform as well the bootstrap in most cases as the estimated variance is larger than bootstrap. The second method is bootstrap resampling where a subsample will be generated by random sampling with replacement from the original sample. Subsample will have the same number of values as original sample. Let's say your friend has 5 cards and you want to generate a subsample using bootstrap resampling method. This is what you will do. Assuming that you and your friend are separated by an opaque partition. You ask a card from your friend, write down the value of the card and pass the card back to your friend. You repeat this 5 times to generate one subsample since your friend has 5 cards. Your friend can give you the same card multiple times, the choice is his. You repeat this sub-sampling say 1,000 times, which means 5,000 times of passing back and forth. If your aim is to find the 95% confidence interval of the mean of your friend's cards, then you calculate the mean for each of your 5,000 subsamples. The standard deviation of these 5,000 means is the standard error, which can be used to calculate the 95% confidence interval of the mean of your friend's cards. You can also see why bootstrap resampling is not feasible to carry out manually. And because each subsample can be different, bootstrap resampling will give a different result, though close result, every time you run it. However, the estimated variance, which in this case corresponds to the standard error, is closer to the actual variance of your friend's cards when compared to jackknife resampling. Now, let us look at how we can use jackknife resampling method to estimate the confidence interval of a statistic, and in this case, the statistic is coefficient of determination, or R-square. I am going to show you how it is done manually. Using the same example as before, you have a set of data and regression is performed. The x and y values are provided and the coefficient of determination, R2, is 0.9139. The purpose is then to find the 95% confidence interval of R2. How can jackknife procedure help me to find the 95% confidence interval of R2, the coefficient of determination? In essence, I will need multiple R2s, and in order to do so, I will generate multiple y values. Since there are 10 data points in the original xy pairs, there will be 10 sets y values, which I term them as y1 to y10. Each of these y1 to y10 will have one value removed. For example, y1 will have the first y value, 32, removed and 9 values remaining. y2 will have the second y value, 14, removed, and so on. Then, I will calculate 10 R2s by taking the original x values with one of the y1 to y10. In this case, the R2 of x and y1 is 0.9041, while the R2 of x and y2 is 0.9156, and so on. Using these 10 R2s, I can then estimate the mean R2 to be 0.9154 with a standard deviation of 0.2151. This can then be used to determine the 95% confidence interval of coefficient of determination. And this is how jackknife can be performed manually. Bootstrap resampling, where a subsample will be generated by random sampling with replacement from the original sample. Subsamples are also known as bootstrap samples. Subsample will have the same number of values as original sample. A statistic, such as mean, can be calculated for each subsample. Normally, we will repeat this subsampling and statistic calculation for more than 1,000 times. Central limit theorem then tells us that the desired statistic will be approximately normally distributed regardless of the distribution of the original population. This meant that the mean of bootstrap means, which is an estimate of population mean, can be calculated. And the standard error of means is just the standard deviation of bootstrap means, which is essentially the standard deviation of means from bootstrap samples. Using this, you can then perform one sample t-test, which was covered in topic 4, regardless of whether the original population where the original sample was taken from is normally distributed or not. So this is how you can use bootstrapping to bypass the need for nonparametric statistical tests. So now let us look at how we can use bootstrapping procedure to perform parametric statistical test on data that may or may not be normally distributed. For example, I want to test whether the mean equals to 35 and I have a sample, which is listed here in yellow. There are 10 data points in this sample. Assuming that this sample shows that the population is not normally distributed based on Shapiro-Wilkes test, which you have learned in topic 2. Next is to generate bootstrapped samples. Each bootstrapped sample also contains 10 data points and obtained by sampling with replacement from the original sample. That is to say, I randomly pick a value from the original sample, say 23, put it back, shuffle, then randomly pick another value, and I happen to pick 23 again. I repeat this until the first bootstrapped sample is done, which is 23, 23, 23, 18, 49, 12, 47, 12, 40, and 10. from which I calculate the first bootstrap mean, which is 25.7. I repeat this step of generating bootstrap samples and calculating bootstrap mean 14 more times to give 15 bootstrap samples with its corresponding 15 bootstrap means. In reality, I will have to do this not 15 times but at least a couple of hundred if not several thousand times. Nevertheless, I use 15 bootstrap samples to illustrate. From these 25 bootstrap means, the mean of means is 27.7. The bootstrap standard error, which by definition, is the standard deviation of the 15 bootstrap means, is 4.40. Using mean of 27.7 and standard error of 4.40, I can test the null hypothesis that the mean is 35 using one sample t-test, which was covered in topic 4. Since by central limit theorem, the distribution of bootstrap means will be approximately normally distributed. One sample t-test with 14 degrees of freedom, since there are 15 bootstrap samples with 15 bootstrap means, gives me a p-value of 0.0597, which is larger than the usual alpha of 0.05. Hence, we fail to reject null hypothesis and accept null hypothesis. Therefore, the mean equals to 35. Hopefully, you can see how we can use bootstrapping procedure to perform parametric statistical test on data that may or may not be normally distributed, and this makes bootstrapping procedure to be very useful in statistical analyses. With that, we come to the end of this topic. Good luck and have fun with more statistics in the future.